right, so today we're going to talk about resolving vectors into components. So you also did this graphically on the summer assignment, but we didn't do it with as much math. So we're going to kind of throw in how we solve these problems. So remember that resolving a vector means breaking it into its components, and those components have to be perpendicular to each other. So breaking a vector into a pair of perpendicular components. So those components can be positive or negative, they can be X or Y, they can be north or south. It just depends on your coordinate system. So what happens in this case is you start with usually just one vector. For example, I could have this vector here, which is like say 5 meters per second, and it's going to have an angle associated with it. So in this case, our angle is going to be 30 degrees north of east. And I just get labeled that over here, 5 meters per second. So the 5 meters per second represents the magnitude of this velocity vector, and 30 degrees north of east represents its direction. So essentially what I have is I have gone east and I have gone north. And so what I can do is I can take that triangle that I have here originally, and what I do is you keep your angle theta there, is you extend out kind of your reference line and drop that vertical down just like you did in the summer assignment to make a 90-degree right triangle. And then I have to make sure that my directions add up. So these vectors that are our components should add up in direction to where I ended up, so that these add up tip to tail. But my resultant vector essentially goes from the start to the end. Now, because this is a velocity vector, I could call this main vector v, and then I could call this vector vx, and this vector vy. So my v is 5 meters per second. And once again, I label my diagrams very extensively when I'm working, and this is 30 degrees. Now, I'm going to draw my little compass here for my coordinate system. So I'm going to do north, south, east, and west. So now I know, just because I have this labeled here, that this angle is 30 degrees north of east. Because remember, the north is where you ended up, and the east is your starting reference direction. So this vector starts in the east and then it goes north. So that's kind of the way to describe that vector. Now, if I wanted to calculate and find these component vectors, I can use my trig functions. So remember that with your trig functions, you have the opposite side, you have your hypotenuse, and you have your adjacent side. Now, if I know my hypotenuse and my angle, I can find my adjacent and opposite sides. Adjacent I could find using cosine. Cosine of my angle theta is going to be my adjacent over my hypotenuse. So if I wanted to find the magnitude, I could just multiply my hypotenuse, and adjacent would equal hypotenuse times cosine theta. So I just know that. I know that the adjacent side is always going to be hypotenuse times cosine theta, so I don't have to start here. I will usually just start here when I'm working problems. You do whichever is more comfortable for you. Now, for the opposite side is based on sine theta when relative to my hypotenuse. So sine theta is equal to opposite over hypotenuse. So that means that my opposite side is equal to hypotenuse times sine theta. So I have basically just defined how to find my two components by using these trig functions. at least the magnitudes of them. So if I wanted to come over here and find Vx, Vx is going to, or that's Vy, sorry, this is Vy. Vy is the opposite side of this triangle, so it is going to be hypotenuse times sine theta. Now, y component is not always the sine, based on sine, because it depends on what angle I'm given. So memorize just that the opposite side of the triangle is hypotenuse times sine theta, not that it's the y component, because it could, the x and y's can change. And then my x component is the adjacent side, so it's going to be hypotenuse times cosine theta. So then I can use those equations. So now I have non-numerically defined how I'm going to solve this problem. So if I was going through to go solve this problem, I would just substitute into those. And if I wanted to find these two components, my Vy would be hypotenuse, which is 5 meters per second, times sine of my angle 30 degrees, making sure that your calculator is in degree mode. You'll find that when you work in pre-cal and calculus at the same time, you spend a lot of time in math class in radians mode. You need to make sure you're in degree mode when you come to physics for most of what we do. And then my Vx component is going to be 5 meters per second for my hypotenuse times cosine of 30 degrees. So if you go through and we can find those values. So I would have 5 sine of 30. So Vy is 2.5 meters per second. And Vx would be 5 cosine of 30, which would be 4.3 meters per second. And you might think, oh, I'm done. Well, you're not done, because these are magnitudes only, and my components are vectors, so I need a direction. Well, based on this map coordinate system here, my x direction is in the east and my y direction is in the north. So with that, I have my magnitude and direction for each of those component vectors. So that's basically what you have to do. It's not that much different in any other cases. You can have components of displacement vectors, acceleration vectors, velocity vectors. We'll have force vectors and all sorts of vectors that we're going to resolve into our components. So this is a really good skill to have. So I hope that gives you a pretty good feel for how to solve these problems. Have a good day.